calculus class, we're going to look at some of these tests for convergence or divergence. So a lot of these tests, again, they don't tell you what the series converges to if it does converge. It just tells you if it does. So it's like a yes/no thing. It converges or it diverges. So it tells us to use the integral test. So from your notes, this is what the integral test says. It says that if, and this is an important thing, f is continuous, positive, and decreasing. So it has to be, can't have asymptotes, but it has to be decreasing. All right. Now it could start off increasing, meaning like it could go like this for a little bit, but then it has to eventually begin decreasing. So if all those things happens, and this would be, that, and technically these would be like Riemann sum type rectangles, but it's like, one of these is the series, or the rectangles are the series, and the
Okay, I found this on the web for what are the rectangles of a series. Check it out.
And the curve is the functions that you're talking about here. So a sub n is given by f of n. So like at the whole number of points we get these heights. That's the rectangles. But the function itself could have numbers in between, and that's the integral that we take. That's the function itself. So that's the visual of it, but here's the nuts and bolts that you got to be able to do the integration. So if I were to graph this, all right, so when I graph it, there it is, I graph it as x instead of n. But when I graph it, I can see that from 0 and beyond, this function satisfies the conditions of the integral test. We have a function that's decreasing, but it's positive and continuous. So because of that, the integral, all right, notice if I plug 1 in here, for n, I have 1 squared plus 9. So when I convert it to this integral right here, I'm going to put 1 to infinity 7 over x squared plus 9. And that's the same thing if I plug 1 into for that x. I would get 1 squared plus 9. So I'm starting at the same point that this series would start. All right, now when I look at the graph of this, there's the function. I can see when I plug in 1, right there, I am continuous. It's falling, meaning it's decreasing to infinity, and it's above the x-axis, so it's positive. So it meets all the criteria for the integral test. So that's what that part. Make sure to check the conditions are satisfied. So it is positive, it's decreasing, continuous, so we can use it. That would be fine if you guys use the table of integrals here. So look, a is 3, and we got a 7 here, so we're going to have a 7 multiplied times this. So this is going to be 7 over 3 inverse tangent of x over 3. All right, and we are going to plug in infinity and plug in 1. All right, obviously if you remember from the improper integrals section, that means that we're going to take the limit as b goes to infinity and replace that with a b. So we'll have the limit as b goes to infinity of 7/3 the inverse tangent of b over 3. So b going to infinity, dividing that by 3 is not going to keep it from going to infinity. So this is still the inverse tangent of infinity. And if you recall, that's pi over 2. So this is 7/3 times pi over 2 for that part. And then the inverse tangent of 1/3, that's not a special angle, so we would just leave it as that should be inverse tangent of 1/3. All right, you can leave it like that. You can also factor out the 7/3. So because that is a finite value, and that's what we're doing here is determining does this integral converge, and because it does, we get a integral that converges, then that means the series converges. The series converges. Now it does not converge to this. This is not what the series converges to. Okay, the integral proves the series converges, but it does not suggest that the series converges to the same thing that the integral converges to. That's the big thing that you got to get down with the integral test. It just is like a yes or no thing. The integration, the integral that we get converging proves the series converges. The integral diverging proves the series diverges. But when the integral converges to a value, the series does not necessarily converge to that.